So, welcome back to the course on computer network and internet protocols, and in the last class we are discussing about socket programming. In today's lecture we will again continue with the socket programming in details. So, in the last class we have looked into the UDP socket, we have looked into the basic of socket programming along with the UDP server and the UDP client in details, that how you can use this concept of datagram or the datagram socket to transfer data or receive data using UDP protocol. So, today we will look into how you can do the same thing using TCP protocol, and we will look into different variants of TCP server. So, first let us look into the demo of demo about the TCP server and the TCP client. So, first we will look into this TCP server, the source of the TCP server in details. Well, so do not get confused with this end arrow. So, this is a C program, do not get with this end arrow and this dot, just a formatting we have used for our clarity of writing the code. So, this is your C code. So we have this network related headers which are being included, followed by the main function. So, in the main function, similar to the UDP1 UDP server that we have discussed, we are declaring the server address first, server address variable of type struct socket in, and file descriptor to store the socket ID that will be created. And this is the syntax that how you should use the code. We are taking the port number from the command line argument, and then we are taking the port number from command line argument, and we are creating the socket by this socket system call. So, this socket system call similar to the earlier case, it will take AFINet as the protocol family, but the socket type is now sock stream instead of sock dgram. So, and finally, this protocol field is 0, and as I have asked you earlier, that try to explore that why we mostly use protocol family protocol type as 0. Now, if the socket is not created successfully, some error message that is getting printed, and after that we are initializing the server address field, the server address family, protocol family, we are setting it as AFINet because we are going to use the IPv4 address, followed by the server address. The server address we are taking it as inaddr_any. So, this inaddr_any will help us to take the address of the local host. Then we are providing the port number which we have taken from the console. So, we have initialized the server address. So, once you have initialized the server address, you have to bind it with the socket. So, we are making a bind system call. So, the bind system call may fail sometime, because if you are going to use the same port number which is being used by another application, there are other reasons where a bind call may fail. So, if the bind fails, we are having a error message that it is failed to bind, otherwise the bind was successful. And the bind is taking the format as we have discussed earlier, the socket file descriptor, the address of the server and the size of the server address variable. Now, we are making a listen call. The listen call here we are providing the socket and socket file descriptor, and we are specifying 5 as the maximum number of connection that can be backlogged in the listen call. So, this concept of backlog connection is that the server can handle one client at a time. So, whenever it is taking the connection from one client, during that time multiple client can again try simultaneously. Just think of a scenario of a web server where thousands of requests are coming to the web server per second. So, during that time when the server is busy in executing this say the listen call for one connection, during that time the other connection will get backlogged. So, this parameter 5 it specifies how much such connection can get backlogged. So, after that we similar to the earlier, we are making a call to this setsock opt function to provide this facility of reuse ADDR, so that we can use the port number for multiple codes together. And after that we are declaring a receive buffer to store the incoming data in a string format, the buffer length and receive length that to indicate how much data we have received. And we are declaring this client ADR variable that struct sock ADDR type of variable to store the client address, and this len this variable store the address of the client. Now, inside the loop what we are doing, we are making the accept call at the server side. Now, TCP is a connection oriented service, that is why you have to make the connect call from the client side and the accept call from the server side to initiate the connection, which will utilize the three-way handshaking of the TCP protocol. So, after we are making the accept call we are passing the parameter as the socket file descriptor, the address of the client and the length of the client address. If there is an error, so all these function, if there is an error, they return some negative number. So, that is why you can check the return value. If it is less than 0, that means certain error has occurred. Okay. So, after that, once it is accepted the connection, we are printing that we have received a new connection from the client address. We are specifying the client address and the client port. So, from that particular client address and the client port, a new connection has been received, and after that we are having a loop where we are receiving the data from the new socket that has been created. Now, here also while you are making the accept call, in the accept call it returns a new file descriptor, and this new file descriptor will initiate this end-to-end connection between a server and the client. So, it returns a new socket descriptor that will be used in the in sending or the receiving data, which is specific to a pipe or specific to a socket between a server and the corresponding client. So, we make this receive call to receive the data. We provide this new socket file descriptor that you have received after making the accept call, and then the receive buffer to store the data, the buffer len, and this entire call will return the amount of bytes that have been received. So, that will return by the receive call and it will store inside the receive len function. Now, if receive len is equal to 0, that means you are not receiving any data from the client. So, you can close this particular connection. Otherwise, you get the data and print that data that you are receiving at the server side. And after that, we are actually whatever data we have received, we are echoing same data to the client by using this send function. Okay. So, you have received the data which is stored in the receive buffer, same data is echoed back to the client side. So, this is my code for the server side. Now, let us look into the code at the client side. Okay. At the client side, things are pretty similar. On we are declaring the socket, we are creating a new socket, and after creating the new socket, we are getting the here in the client side, we are getting the server IP or the server host name and the port from the command line argument. So, we are using that command line argument to create the server address. So, we have declared the server address as a variable, as a struct socket ADR in variable. So, inside that we are putting the server address. So, we are getting the server IP. So, get host by name, this particular function return the host IP from the host name. So, we are getting that, and then we are putting that server address in this server ADDR variable. So, we are initializing this server ADDR variable with all zeros, that is the initialization, that the server address family, that is AFINet, to use the IPv4 address, then this HADDR and this particular field we are using to provide the corresponding server address and the port number. Now, we are making a connect call to initiate the connection at the client side. So, the connect call, it sends this socket file descriptor along with the server address that we have seen earlier. So, it initialized the connection to the server using the TCP three-way handshaking procedure. Now, after that, after the connect system call has made, you have initiated the connection to the server, then you make the call to the send function to send the data. So, we are creating a message called hello there. This particular message we are sending to the server, and as you have seen in the server code that the server will actually echo back that particular thing to the client. So, after you are sending that, you are receiving the message. So, we are declaring a buffer as a character array. We will get the data in the form of a character array or a string. So, we are declaring that buffer for that, and after that we are making a receive call. This receive call over that socket file descriptor that will get the data from the client side. So, from the server side. So, as you have seen in the server code, the server will actually echo back the data that you are sending. So, here you are sending this hello there function, same hello there function will be echoed back. So, you will receive that data, and after receiving that data, you print that particular data at the console. So, that is the code for the client side. Now, let us compile and run these two things. So, first let us compile TCP server. And compile TCP client. So, first we will run the server. So, we need to specify the port address. So, we are giving port address as 2444. The server will, now the server is running there. So, once the server is running there, from the client side, we can give. So, the server is running in my machine. So, I am giving the server host name as localhost and the corresponding server port that we have used here 2444. So, it has received the message, and at the server side you can see that it has received a new connection from the local machine. The IP is 127.0.0.1 and the port of 47676. So, it has received this hello there message, it has echoed it back, and the client has received that message. So, if you again run the client, again it has received the hello message, and you can see that it has received another connection at a different port 47678. So, if you run it again, you see that it is again using a different port 47680. So, the same thing as you have seen for the UDP server case, that the server is announcing itself to a well known port, but the client need not to do it. So, the client is actually using some random port to initiate the connection from the client side, and that particular port value we can see here. Now, this is a kind of TCP server and the TCP client implementation, where in the TCP server implementation we call it a kind of iterative server. Why we call it iterative server? Because if you look into the code, let me open the code again. So, here you will see that these connections. So, here we are making a while loop, and inside this while loop we are accepting the connection. So, how this entire thing will work? If multiple client requests are coming simultaneously, then one client will be taken, that connection will be taken, that will get executed, then the next client will be taken, that will get executed, then the third client will be taken, that will get executed, and that way this entire thing will go on. So, that is why we call this kind of server implementation as an iterative server implementation, where the client requests are executed one by one. So, now we will see that so one thing is that this kind of iterative server implementation is not very useful when you are trying to design a server like a web server, while you can get thousands of requests per second. Now, if that is the case, then you have to handle the client request in parallel, otherwise the server will not scale up. So, we will now see that how you can actually implement a parallel server using this help of socket programming. as well as some concept of your operating system level programming and your operating system concept of multiple processes. So, if you do not have a understanding of this operating system concept of processes, I will suggest you to look into this process concept in operating system and look into it in details. So, we will use this concept of process in the operating system to look into this implementation of concurrent servers or the parallel servers. So, as we have looked earlier that you are creating multiple such connections. We have already looked this socket programming framework or the APIs. Now, the concept of concurrent server is something like this, where multiple clients are trying to connect to the server simultaneously. Now, if multiple clients are trying to connect to the server simultaneously, then how will you handle that thing? So, one way is to handle it is using the iterative server, but as we have seen that the iterative server may not be very useful. So, we implement the parallel server using this concept of multiple processes in operating system. So, the idea is something like this: you have a server process which is having the parent socket, then you can make a fork system call. So, in operating system, this fork system call creates a child process. So, what you can do that once you are accepting a connection, then you can make this fork system call to create a child process which will actually handle the data transmission and data reception from that particular child connection. If you are not doing that, if you are doing it in the earlier way that we are doing inside a while loop in the form of a iterative server, then the time until a particular server is keep on sending and receiving data, it is not closing the connection. Up to that point, the connection will remain blocked. So, the server will not be able to handle the second connection until the first connection is complete. So, that is why the idea is that whenever a new connection is coming, you make a fork system call, and after making a fork system call, have a child process. That child process that is a part of the server process, but that will create a child socket. It will. So, we have seen that after you are making a accept call at the server side, it returns a new socket identifier which is used to send or receive data to the client. So, you pass that particular new socket file descriptor to the child socket which will handle data transmission and reception in parallel. So, the broad idea here is that you get all the connections one after another, but do not wait for the send and the receive functionality of an individual connections and keep other connections in the waiting queue. So, you create a child process, and that child process will or we call it as the child socket that will handle the send and the receive data functionalities of individual client request that you are getting. So, that was our implementation of the iterative server that we have done. We have a while loop. Inside the while loop, you are making an accept call, then you have the send and receive, and it is inefficient because until you are complete with that send and the receive functionalities, you will not be able to come out of that and get or make the accept call again to accept the new incoming connection. So, if you look into that how iterative server works, that the listen call, it sets a flag that the socket is in the listening state and set the maximum number of backlog connections that we have seen earlier. Then the accept call, it blocks a listening socket until a new connection comes in the connection queue and it is accepted. So, this accept call is a blocking call. So, the system will keep on waiting here until you are making a connect call from the client side. So, it is a blocking call. Now, once this new connection is accepted, then the new socket file descriptor, say the connection FD, it is written, which is used to read and write data or to send and receive data to the connected socket. Now, all other connection which comes in this duration are backlogged in the connection queue, because the process is busy inside this while loop to send and receive data. So, once the handling of this current connection socket is done, current connected socket is done, then the next accept call accept the next incoming connection from the connection queue if there is any, or blocks the listening socket until the next connection comes. So, once the execution of this while loop complete, then only you are coming in here and accepting the next connection. So, everything is actually blocked on the send and the receive call that you have there, you have there at the this particular while block. Now, we extend this iterative server to a concurrent server. So, our idea is that the parallel processing of each incoming socket, so that the accept call is executed more frequently. So, what we do here you see that after we are making this accept call, which is returning a new socket file descriptor, then we have successfully accepted a client connection, then we making a fork system call. So, this fork system call at the parent process, it returns the ID of the child process, and at the child process it returns 0. So, whenever you are making this fork system call, and if the fork system call is returning 0, that means you are inside the child process. Now, this child process, what it does, it closes the original socket, the server socket, and it will use this new sock FD that you got to send and receive data. So, you close the old socket, since all communication will be through the new socket, and then you initialize the buffer, copy the message to it, send or do the receive, whatever you want to do. Now, what will happen here, that whatever is there inside this fork system call, inside this fork block, in this if block, that will get executed in parallel. So, in the parent process will not, so for the parent process this will return false, because the parent process fork returns the ID of the child process, and in the child process fork returns 0. So, in the parent process you will return back, and the parent process will again come here and make the next accept call. So, the parent process now do not need to wait for this send and receive functionalities, which will be handled by a child process. So, now let us look into the demo of this one. So, here we do not make any change in the client implementation. The client implementation remains as it was earlier. We only make change at the server implementation. So, at the server implementation, so the change that we have made, the entire code is similar. If you look into that, we are declaring this server address followed by a socket call, then initializing the addresses at the server address field, making a bind call, making a listen call to broadcast the, or not to actually broadcast, it may not be a correct term, to announce the port where the server is actually listening, and after that making that set sock opt call as earlier. And then inside this while loop, where you are accepting the connection, we are accepting a new connection, and it is going to this child FD. We are creating a new file descriptor. After that, you see we are making a fork call. So, you look into this statement, int fork return equal to fork. So, we are making a fork call which will create a child process. Now, I will suggest you to look into this operating system concept in details. We do not have scope to discuss that. The idea here is that whenever you are making a fork call, this entire code will be copied to the child process as well. So, the child process, what it will do, in the child process the fork call will return a 0, and in the parent process the fork call will return the ID of the child process. So, if you make a if loop with this return value, if the return value is 0, that means you are inside the child process. So, inside the child process, this part of the code will get executed. Now, you see this, the second while loop that we had, which actually deals with sending and receiving data, it is inside only the child process. So, it is inside this if block. Here we are making this receive call and send call, and we are having that handling in parallel at the server side. So, in the server side, this particular if block will not get executed, because in the server in the parent side, parent socket, this will not get executed because the parent socket will return the ID of the child. So, it will be not equal to 0. So, this part will only execute at the child process. So, the child process is now dealing with sending and receiving of the data, but the parent process can come out of that. The parent process is not getting blocked in this second while loop, it can directly come out and accept the next connection. Now, let us run it. So, okay, let us first compile it. -o, naming it as fork server, and running the fork server here. Okay, we have to give the port. Now, this time say give the port as 2555. So, my server is running, and the client is the same TCP client that we used earlier. So, let us initiate a connection from here, another connection say from another tab. So, you are not doing much task. So, you will possibly not get a feel of this parallel execution, but what is happening there, a new child process gets created and it handles this individual request that we are sending there. So, you see that we have made some client execution here in this tab and as well as in the another tab, and correspond to that you are getting the connections at different port, and they are getting executed in parallel. Now, this handling is done by a child process rather than the original parent process. Okay. Now, we have another interesting thing to discuss. Okay. So, what we have seen till now that we can do a kind of server implementation, concurrent server implementation. Now, think of an application something like that, a kind of peer-to-peer chat application. So, multiple people they want to send or receive messages to each other. Now, in this particular case, what may happen that we do not have any central server to control the chat message delivery. Every user runs its own chat server. That means, it runs a TCP server for incoming connections and messages. Now, in Unix, it maintains every connection as a file descriptor that we have already seen. Now, at that time in a chat server, you have a typical requirement that you need to also read data from standard input. So, you need to type something. So, when you are receiving a message, during that time say you are typing something. Now, whenever you are typing something, that standard input, it is again a file descriptor. So, in Unix everything is a file, a socket is represented by a file descriptor, and at the same time the input from the keyboard, that is also represented as an file descriptor by this stdin file descriptor. Now, in that case the question comes, how will you handle it? Because your data is coming from multiple places, you are getting data from the socket as well as you are entering data from the keyboard. How you actually switch between this multiple thing where this message communication is asynchronous. So, you can receive a message while you are doing the typing. So, okay. So, for that we use this concept of the select system call, which is again an operating system level system call. So, this select system call, it selects from multiple file descriptor, which is a concurrent way to handle multiple file descriptors simultaneously, even from a single processor thread. So, you can get the data from the socket, which is one of the file descriptor, as well as the keyboard file descriptor simultaneously. Now, what we have seen that what happens in an iterative server implementation that we have done earlier, that the accept call is blocked until you have completed the read and the write calls. Now, what if you do multiple read and write activities after accepting an incoming connection, that the other connections are blocked and waiting for the connection queue, they may get stopped. Now, select is the way to break this blocking. So, one way to break the blocking is using this parallel implementation. Another way to do the thing is to use the select system call. The advantage with this select system call is that you do not need to create multiple child processes now. No, you do not need to worry about the zombies. So, child process has always a problem that if you are if sometime the parent process get killed or the parent process stops, then the child process becomes zombies. So, with the select system call, you do not need to worry about these zombies. So, you can possibly manage resources more efficiently. So, this select system call, it is nothing but a multiplexer. So, what happens that you have multiple file descriptors, you have certain signals and a timeout, and out of this multiple file descriptor, it selects one of the file descriptors. So, it finds out that among this file descriptor which one is currently active, and it select that particular file descriptor. So, here is the format of the select system call. In the select system call, you are providing the number of file descriptor, it is the highest number of file descriptor in any of the 3 sets plus 1. We have 3 different sets of file descriptor, the read file descriptor to read something as an input, the write file descriptor to write something at the output, and except file descriptor to handle the exceptions. So, these file descriptors are a kind of structure called FD set, and we have a timeout value. So, the timeout value is that if you are not getting anything from this file descriptor for this timeout value, so it will come out of the things. So, it is actually providing you a synchronous I/O multiplexing over asynchronous input. So, as we have mentioned earlier that your input can be asynchronous, you can get a message over the socket while you are doing the typing, but it provides you a multiplexing to select either the keyboard or the socket at one time instance. So, we have 3 different file descriptor. The read file descriptor will be watched to see if characters become available for reading. The write file descriptor will be watched to see if the space is available for write, and the exceptional file descriptor will be watched for exceptional condition. Now, we have a timeout value, the interval that select should block waiting for a file descriptor to become ready. Now, the select call remain block, either a file descriptor becomes ready or the call is interrupted by a signal handler or a timeout expires. So, in any of the cases it comes out of the select. So, whenever one of the file descriptor becomes ready, it comes out of the select call. If that particular call is interrupted by some other signals or the timeout happens. So, this is the procedure to set the timeout. You provide the value in the form of second and microseconds. Now, how do you pass the file descriptor to select? So, for that what we do, we first initialize the file descriptor set FD set, which is a bitmap of fixed size with this FD 0. Then we make the call to FD set. So, this FD set selects a file descriptor, say my socket that I have defined, and the corresponding file descriptor which where the socket is getting added. So, this particular bit corresponds to this socket file descriptor that will get set. That means, some data is available there. Okay. Then you make the select call. So, how select works? So, it loops over all the file descriptor. For every file descriptor, it calls the file descriptor poll method. So, this poll method is to check that whether something is available to or some event is waiting on that file descriptor. So, it will add the caller to that file descriptor wait queue and return which events currently apply to that file descriptor, whether it is file descriptor is readable, if it is a read file descriptor, whether it is writable, if it is a write file descriptor, or some exception has happened. Now, if any of the file descriptor matches the condition that the user was looking for, read, write or exception, then the select will simply return immediately after updating the appropriate file descriptor set that the user passed. And if not, the select will go to sleep for the timeout value. Once the timeout occurs, it will come out of that select call, and if some other events happen within that timeout event, it will make this FD set and come out of that. And during that interval, if an interesting event happens to any of the file descriptor that select is waiting on, that file descriptor will notify its wait queue. So, this will cause the thread sleeping inside the select to wake up, and it will repeat the above loop and see which of the file descriptor are now ready to be returned to the user. Now, the return value of the select, we have 3 values. If it is -1 means some error has encountered, 0 means that the timeout has happened, and greater than 0 means that the number of sockets that has the event pending, like read, write or exception. So, for how many sockets that event is pending, whether you are going to read or write or having certain exception. So, after select returns, you can use the function called fd_set to test whether a file descriptor is a part of the set. So, you can check whether a file descriptor has been set or not. If the file descriptor has set, that means you have something to read if it is a read file descriptor, or you have something to write if it is a write file descriptor. So, let us look into a code which uses this select call. We will use the same TCP server implementation with this select. So, the base part of the code is same as earlier. We are declaring the server address, the bind call, the listen call at the server side, the set sock opt call, and after that we are declaring the file descriptor. So, here we are declaring that we can have a maximum of 16 different file descriptor, and this fdlen returns that how many such file descriptor are currently set or currently active. So, we are declaring the set of file descriptor and the maximum file descriptor, which is equal to the current socket file descriptor. Now, inside this while loop, we first initialize the file descriptor. We are here only going to use the read file descriptor because we are going to read data from the socket, and we are setting through this fdset call, we are setting the read file descriptor corresponds to the socket that we have defined, on the socket where the server is actually listening. Now, we are looping over the available file descriptor. So, here the idea is that whenever we are getting a new connection, we are adding it up inside the file descriptor, inside that file descriptor set. Okay. After that, we are making a select call. So, as we have seen earlier that here we are not giving any timeout value because we are not giving any timeout value. So, it will keep on waiting for infinite duration. Whenever some event will occur, then only it will come out. So, we are initializing with these read file descriptors. So, whenever a new connection will come, it will come to this read file descriptor through this loop, and then it will keep on waiting here. When some event will occur, that poll function will get triggered, and that poll function will return whether certain event is there in the read file descriptor. Certain event means whether that particular socket is ready to read the data. And after that, if select returns, that means some socket is ready for reading the data. Then you check using fd_set whether that particular socket is ready to read the data. If that socket is ready to read the data, then you make a accept call. To accept that particular connection. That means some connection is waiting. You accept that connection, and after doing that, the way we are closing the child file descriptor, and then add that particular thing to that file descriptor loop. Then in this fd_set, you loop over all the file descriptor that you have been added. So, here earlier what we are doing, that whenever some new connection is coming, using that select call, we are checking that some new connection has arrived. So, if that is a new connection, we add that new connection to the set of file descriptor that we have. Otherwise, some file descriptor from the existing file descriptor is ready to read. So, what we do that we check, we loop over the available file descriptors that we have, and the file descriptor that is currently ready. On top of that, we make the receive call and get the data, okay, and then return back the data there. So, if that receive len is equal to 0, that means you are not receiving any data. So, you close that file descriptor and clear it from your file descriptor set. So, that is this entire idea, and after that you send the data in our normal procedure. So, the idea is that whenever you are getting a new connection, we are adding that new connection in the set of file descriptors, and then we are looping over that file descriptor to find out which one have certain data, and if someone has certain data, we are sending back that data. Now, let us run this code. First compile it. Again, we are going to use the same client implementation that we have. The client implementation, we are not making any change. So, now my server runs over select, I am giving a port 2666, it is running from the client side. Okay. You send the data, you send something, it has received that, then once the task is done, it has closed that particular connection. Again, you can execute it, you see it is from again a different port, the same thing we are keep on observing. It has received the data, echoed it back to the client, and closing that connection, that particular connection. And well, one thing just I wanted to show that if you try to connect to a port where the server is not running. So, the server is now running at port 2666. Now, if you try to connect it, it will get a connection refused message from the connect call, because none of the server is currently running at the port 2555. So, this is all about our discussion on TCP server. I was quite fast in describing the things with the assumption that you have a basic knowledge of C programming and operating system. We will share all the codes with you, and I will suggest you to browse the code and look into the tutorials that we have shared. And if you have any doubt or anything, feel free to post the questions in the forum. With this particular socket programming, you can develop your own applications. You can even implement the chat server application that we are talking about. So, I will suggest you to look into that and implement multiple such applications on your own with the help of these different variants of socket programming. So, thank you all for attending this class. From the next class onwards, we will go for again the theoretical aspects of the TCP/IP protocol stack. So, thank you all for attending this class.